Hello everybody, I would like to introduce the analysis of variance for the completely randomized block design, which is abbreviated by CRBD. This is the question I will examine. We have an experiment was performed to determine the effect of 4 different chemicals on the strength of a fabric. These chemicals are used as part of the permanent press finishing process. 5 fabric samples were selected and a randomized complete block design was run by testing each chemical type once in random order on each fabric. The data are shown below. Test for the differences in means using ANOVA with alpha equal 0.01. So this is the question. We have 4 treatments which are using the 4 types of different chemicals, and we have 5 samples of fabrics. We have fabric 1 and fabric 2 up to fabric 5. And the records here represent the strength of the fabric after the completion of the treatments. So for example, for this unit or this subject, which is belonging to fabric number 1, this is treated by chemical A, and the value of the strength after the treatment is 1.30. So we need to make the calculation by hand using the block design. First of all, let's understand the block design. For this experiment, we have experimental units equal to 20, which means that we have 20 fabrics which are different from each other. And for each fabric, we have number of units equal to 4. So this is the experimental units, or sometimes it's called the subjects, which is simply 20 different fabrics. First of all, in order to conduct the ANOVA for the blocks design, we need to rearrange or regrouping the experimental units. For example, we group the fabric 1 in one block, which is called block 1, and we group fabric number 2 in another separate group, which is called block 2, etc. So as you see here, inside the block itself, there is a homogeneous between the units, but between the blocks there is a heterogeneous between the units. So the purpose of rearranging the experimental units into blocks is simply to reduce the value of the variability for the error by reducing the variability inside the blocks. After that, we have the randomness process. Simply for each block, we assign the 4 treatments in a random manner to the units for each block. For example, for block 1, the first fabric here, by random assigning, will be treated using the chemical C, while for the other fabric 1 inside block 1, this fabric will be treated using the chemical A, etc. So this is the meaning of the random or the completely randomized. So the randomization occurs in 2 processes. The first is the process of the selection of the experimental units or the samples, and the second process of the randomness is the assigning in a random manner each unit in each block to the different treatments. The word completely randomized design, the word completely means that each unit in each block will be treated using all different types of treatments. So this is the meaning of the word completely, which means for each block we are using all the different types of treatments. So regarding the units that will be treated by using chemical A, this is the first one, and this is another one. This fabric exists in the second block. This is the third one, which is a fabric inside the third block, and this one, which is inside block number 4. And finally, we have this unit here, which is inside block number 5. What to do now is to gather all of these units for each treatments. So this is the process of gathering units to treatments. So we have 5 units will be treated using chemical A, and all the 5 units comes from all the blocks. This is the recording of the fabric strength after the treatments. For example, for this unit or this fabric inside block number 1, it is treated using chemical A, and after the treatment by using this chemical, we measure the strength of this fabric. So it is 1.30. This is the block design ANOVA table. Regarding the sources of variation, we have a variation for the treatments, which is our interest, and we have a variation inside the blocks, and we have a variation for the error. Then we will calculate the degrees of freedom and the sum of squares, and then we will calculate the mean square. Then simply we can determine or calculate the statistic f or calculated f, and we will compare this calculated f with the critical one using the f distribution table. So we need to fill all of these cells inside this table. Before starting the calculations, we need to understand some details regarding the experiment we have here. First, regarding to the independent variable or the factor, we have the effect of the chemicals on the fabric strength. So this is the independent variable or the independent factor. Regarding the dependent variable, it is simply the strength of the fabrics after being treated by using the chemicals. The controlled variable by blocks is the fabric type. So as you see here, we gather the experimental units by grouping them inside blocks. So for each block, the variable is homogeneous, while between blocks, there is a heterogeneous between the blocks. Regarding T represents here number of treatments. So as you see here, we have 4 different types of chemicals from A up to D. So the value of T is equal to 4, which are simply chemical A, B, C, and chemical D. Regarding for R represents here the number of blocks. We have 5 blocks. Block 1, 2, 3, 4, and 5. In order to calculate for the total units, we simply multiply the value of T by the value of R to get the total observations. So the total observation is simply 5 times 4, which is equal to 20. First, we should state the hypothesis. We are interested in 2 sets of hypotheses, one for treatments and the other for the blocks. Regarding the treatments, the null hypothesis for the treatment states that there is no difference between the mean of the fabric strength by using chemical A, which is the same as the mean using chemical B, which is the same as the mean for the fabric strength using the chemical C, same the mean by using the chemical D, or simply we can state that all means are the same. For the alternative hypothesis, it states that at least one mean of the treatment is different from other means. So we need to test these hypotheses for the treatments, and regarding to the blocks, the same way we have the null hypothesis for the blocks H sub 0, which states that the mean for block 1, which is simply the mean of the fabric strength inside the first block, block 1, is the same as the mean in block 2, same as in block 3, same as in block 4, same as in block 5, or simply we can state that all means are the same. And regarding the alternative hypothesis, it states that at least one mean of the blocks is different from other means. So we need to test all of these hypotheses. First, we can simply calculate the degrees of freedom. The degree of freedom for the treatments is simply equal to the number of treatments minus 1. The number of treatments is simply 4. Here we have 4 treatments. So the degree of freedom for the treatments is equal to 4 minus 1, which is equal to 3. Then we can simply calculate for the degree of freedom for the blocks by saying that the degree of freedom for the blocks is equal to the number of blocks minus 1. We have 5 blocks, so 5 minus 1 is equal to 4. This is the degree of freedom for the blocks. Regarding the degree of freedom for the error, simply we multiply the degree of freedom for the treatment by the degree of freedom for the blocks, which is equal to t minus 1 multiplied by r minus 1, which is simply equal to 3 times 4, which is equal to 12. So this is the way how to calculate for the degrees of freedom for the treatments and the blocks and the error. Now regarding the total degrees of freedom, we can simply sum all of these values to get the degree of freedom total, degree of freedom for the treatments, plus the degree of freedom for the blocks, plus the degree of freedom for the error. This is the df for treatment, this is for the blocks, and this is for the error, and the total is equal to 90. Another way to calculate the degree of freedom total is to subtract 1 from the total observation. So you can say that the degree of freedom total is simply equal capital N minus 1. And capital N here represent the total observation or the total experimental units. So we have 20 experimental units minus 1, which is equal to 19, same like what we get by using the formula. Now we can fill in all of these degrees of freedom inside the block design ANOVA table. This is the df for the treatment, this is for the blocks, this is for the error, and this is the total. Now we will calculate the value of the SS, sum of squares, Notice that almost the grid time is consumed by using the formulas to calculate for the SS. Before starting the calculation for the SS, first we can simply calculate the correction factor. The formula of the correction factor, simply we get the sum of all the observations, we square it and divide it by the number of the experimental units, which is equal 20, or same multiplying T times R. T represents the treatments or number of treatments, and R represent the number of blocks. Notice that I represent the treatments and J represents the blocks. For example, this record here, 1.30, it is X for I equal 1 and J equal 1. So this is belonging to X11. This record here, using chemical A, and it is inside block 2, so it is X12. Regarding this value here, it is inside the treatment 3 and in block 3, so this is X33. Regarding the chemical A, for example, these are all the records we are interested in. So the sum of all of these recorded has been calculated. So it's 5.70. This is the sum for treatment 2. This is the sum for treatment 3. And this is the sum for the last treatment, which is treatment 4. So now we can calculate the correction factor by taking all the records or all the observations. We have 20 observations. We then square it, divided by number of observations or number of experimental units, which is equal to 20. And 20 is simply comes from multiplying the number of treatment, which is 4, by the number of blocks, which is 5. Notice that the total observations has been calculated, so it's 39.20. So we square the 39.20 divided by 20. So simply we can get the value of the correction factor, which is equal to 76.83. We need this value of the correction factor in order to calculate for the SS. Now we can simply calculate the total sum of squares, which is SS total, simply by using this formula. So SS total is equal to the summation of the squares of the observations all minus the correction factor. So this is X11 square This is x12 square. This is x13 squares plus plus. And finally, we have here, this is x45. We square all of these values and subtract the correction factor. So if you proceed, you can get the value of the SS total, which is 25.69. So this is the way how to calculate for the SS total. Now we can calculate for the sum of squares of the treatments or the SS treatments. As we said, for the first treatment, this is the sum of the records for treatment 1, and this is for the second treatment, this is for the third treatment, and this is for the fourth treatment. So we should square all of these values and take the sum of these divided by R. R here represent the number of experimental units which is treated by chemical A. Notice for chemical A we have these records, and if you count for the observation of these records, we have here 1, we have here another 1, so 2, 3, 4, 5. And 5 is simply the number of blocks, which is R. So this is the sum for the first treatment, or x1. This is the sum for the second treatment, which is x2. We square it. This is for the third one, and this is for the fourth one, divided by 5, and this is the value of the correction factor. If you proceed, you can simply get the value of the SS for the treatments, which is equal to 18.05. Now we'll calculate the sum of squares of the blocks or SS blocks. Notice that for block 1, these are the records for block number 1. And actually we are interested in the sum of all of these values for block 1, and this is for block 2, this is for 3, this is for the 4 one, and this is for the last one. So we should square all of these 5 values and make the summation and divide it by T. T here represents number of treatments. For example, for block 1, if you count number of units inside block 1, we have here 1, 2, 3, and 4. And 4 is simply the number of the treatments. So this is x1 for the block 1, we square it. This is x2 for block 2, square it. This is for the third one, this is for the fourth one, and this is for the last one, divided by 4, number of treatments, minus the correction factor. You can simply proceed. You will get the value of the SS for the blocks to be 6.70. Now we can calculate the SS for the error. We already calculated the value of the SS total. This is already known, and the same for the SS for the treatments, and the same as for the SS of the blocks. So SS error is the only unknown in this formula. So you can keep the SS error in one side and move the other values in the opposite side, so the sign will be opposite. So SS for the error is equal to the SS total minus SS treatments minus SS for the blocks. This is the SS total, this is the SS for the treatments, and this is the SS for the blocks. So the value of the SS for the error is 0.94. So by this we have calculated all the values for the SS. We can simply now fill all of these values inside the ANOVA table. This is the SS for the treatments, this is for the blocks, this is for the error, and this is the total SS. Now we can simply calculate the value of the mean squares by dividing the sum of squares by the value of the degree of freedom. So to calculate the mean square for treatments, which is MS treatments, it's equal to the value of the SS for the treatments divided by the degree of freedom for the treatments. This is the treatment SS, and this is the treatment degree of freedom. So this is the value of the mean square for the treatment. It's equal 6.02. Now we need to calculate the mean square for blocks, or the MS blocks, the same way. This is the value of the SS for the blocks, 6.70, and this is the value of the degree of freedom for the blocks, which is 4. So the value for the mean square of the blocks is equal to 1.68. For the mean square for the error, or MS for the error, the same way. This is the SS for the error, and this is the degree of freedom for the error. So the mean square for the error is equal to 0.08. Now we can simply calculate the value of the F statistic. The formula to calculate for the value of F is simply to divide the mean square by the mean square of the error. So for the treatment, the calculated value for F for treatments is equal to the mean square of the treatments divided by the mean square for the error, This is the value of the MS for the treatment, and this is the mean square for the error. So the value of the calculated F or statistics F is equal to 75.25. Notice the value of the F treatment is extremely great. So the chance to reject the null hypothesis will be very big. By the same way, we can calculate the F statistic for the blacks. This is the formula, and these are the values. This is the MS for the blacks, and this is the MS for the error, and this is the value of the calculated F for the blacks, which is equal to 21. Again, notice that the value of the F for the blacks is significantly great. So again, the chance to reject the null hypothesis will be great. Now the remaining values is to determine the value of the F critical for both the treatments and the blacks. To find the F critical for the treatments, we need first to know the value of the probability, which is simply the area right to the F critical for the treatment, which is simply equal to the alpha, which is the significant level, and it is given in the question to be 0.01. We need to know the first degree of freedom, df1, which is called the degree of freedom in the enumerator, which is simply the degree of freedom for the treatments, which is equal to 3, and the other value of the degree of freedom is the second one, which is called the degree of freedom in the denominator, which is simply the degree of freedom for the error, and it is 12. So we need to calculate, or sorry, we need to determine the value of the F critical for the treatment for probability equal to 0.01, and first degree of freedom equal to 3, and second degree of freedom is equal to 12. We can simply return to the F distribution table for a probability of 0.01, same like what we have here. This is the distribution of F table for 0.01 level of significance. In this row, we should have the degree of freedom for the treatments, so we have 3, and in this column here we should have the second value of the degree of freedom, which is the degree of freedom for the error, which is 12. So the intersection between these two values is simply the value of the F critical, which is 5.95. So the F critical for the treatments for probability 0.01 and degrees of freedom 3 and 12 is 5.95. So we fill this value inside the block design ANOVA table. The same way, to get the F critical for the blocks, we have the probability, which is equal to alpha 0.01, and for the first degree of freedom, it is the degree of freedom for the blocks, which is equal to 4, and for the second degree of freedom, it is the degree of freedom for the error, which is equal to 12. So we need to determine this value of F for probability 0.01 and first degree of freedom 4, and the second one is 12. We can simply use the same previous table, but for the blocks, the degree of freedom is 4, and regarding the second degree of freedom, it is for the error. So the intersection between these two values is simply 5.41. So the value of the F critical for the blocks is, which is the value of F for probability of 0.01 and 2 degrees of freedom 4 and 12, is equal to 5.41. So by this, all the records needed to be filled inside the ANOVA table has been calculated. So now we need to make or to draw a conclusion for our calculation. Simply, in order to make a conclusion, we should compare between the value of the calculated F or F statistic and the value of the F critical. For example, for the treatments, see that the value of the calculated F, which is 75.25, is significantly greater than the value of the F critical, which is 5.95. So for the treatment, we conclude that there is a significant for the treatment because the value of the F statistics is greater than the F critical. So for the treatment, and regarding the hypothesis for the treatments, we reject the null hypothesis and accept the alternative one. And the alternative hypothesis for the treatment states that the means for the treatments or for the 4 treatments are not the same. Regarding the blocks, the same way, the value of the calculated F is equal to 21, and again it is greater than the F critical. So for the blocks, we conclude that there is a significant level, which means that we reject the null hypothesis and accept the alternative one, which states that the means for the 5 blocks are not the same. Actually, we are interested in the treatments, but why we calculate or determine the significance for the blocks? In order to see that our process of rearranging of the experimental units into 5 blocks gives a significance. So for the treatments and the blocks, we have significant at level of or alpha equals 0.01. So for treatments, the F calculated is greater than the F critical. So simply we reject the null hypothesis H0 and accept the alternative one, which means that there is a significant difference between the treatments. And for the blocks, the F calculated is greater than the F critical. So again, we reject the null hypothesis and accept the alternative one, which means that there is a significant difference between the means for the blocks. So this is all about the completely randomized block design, CRD. If you have any comments, please write it down. Goodbye.